Hi, my name is Dr. Trevor J. Kluter, and welcome to Lecture 2 of an Introduction to Finite Element Analysis. The topic of this lecture is 1D springs, and in particular, how you generate the element stiffness matrix of a 1D spring using the unit displacement method. Following that, we also look at how you incorporate the element stiffness matrix into a global stiffness matrix. So why do we start with 1D springs? Because their mechanics is simple. They are the simplest linear elastic structural element in all of finite element analysis, and this allows us to focus on the maths. What do we mean by the maths? What we mean is the computational framework of finite element analysis. Once the maths is settled and the framework is in place, we can focus on more complicated elements. Now, will we ever use finite element analysis to analyze 1D spring systems? Unlikely. It could happen, but you're probably going to be using finite element analysis for more complicated systems. But starting here is very convenient for understanding how finite element analysis fits together. So, this lecture introduces the element stiffness matrix, which will be represented by a small k in square brackets, or by the acronym ESM, and the global stiffness matrix, represented by a capital K in square brackets, or the acronym GSM, and specifically we're going to be generating these using the unit displacement method, or UDM. Let's consider a 1D spring element. In particular, it's going to be constrained to move only in one direction, in this case the x or horizontal direction, those blocks with the wheels below them indicating a restriction to move only horizontally. We're going to identify the element with a square block with a number in it, in this case the number 1. We're going to identify nodes as numbers surrounded by circles. The properties of the spring, in this case the stiffness K, is going to be indicated by a subscript that corresponds to the element number, in this case K1. And forces on the nodes are going to be indicated by the subscripts that indicate the direction x and the number of the node 2. Similarly, the deflections of the nodes are going to be indicated by the direction x and the number 1 or 2, depending on which element or which node it's acting.
A 1D spring element is said to have 2 degrees of freedom. That is, it has 2 nodes, and each node has 1 degree of freedom. In other words, it can move in one sense, in this case, in the x direction, positive or negative. Every other point of the element can be described by interpolation. In this case, the spring deforms in a linear fashion, i.e. the displacement at the middle of the spring will be the average of that of the 2 nodes. More complicated displacement patterns and displacement functions will be defined later on in the course. Basically, what it comes down to is that any configuration of the spring can be captured or described using only the degrees of freedom and interpolation from the degrees of freedom. We can now set up the element stiffness matrix, or ESM. Now, why do we want to do this? It's easier to manipulate many elements in the same framework if we can describe it with respect to an element stiffness matrix. We're going to do this by implementing the unit displacement method, or UDM. Basically, what we're going to do is hold all degrees of freedom as fixed and then move only 1 degree of freedom by 1 unit, while all the others remain 0. Why? Well, once we've done this and we calculate the forces or the reaction forces on all the other nodes, what we have then is essentially the numbers that must go in the column of the element stiffness matrix that are associated with the degree of freedom that we're moving by unit 1. Now, some other authors refer to this as the direct stiffness method, but frankly, I don't know why this is needed. Just call it what it is, the unit displacement method, or UDM. So how exactly does one use the unit displacement method? Well, the first step is to apply your unit displacement. In this case, we are applying a unit displacement of 1 at node 1 and displacement of 0 at node 2. The next step is to calculate the nodal forces. Now, there will be forces at node 1, that's the force required to displace the spring, and it will have an equal and opposite force at node 2 so we can maintain equilibrium. The magnitude of this force will be the stiffness of the spring multiplied by the displacement, which in this case is 1. And this is why we use a unit displacement, because then all that remains in our expression is the stiffness of the spring itself. And that'll be very useful, as you'll see in a little while. So when we interpret this, the force node 1, F subscript 1 must be positive K, it's in the positive direction, while at node 2, F2 must be minus K because it's opposing the force at node 1. The next step is to try and interpret the nodal forces using matrix notation. We want to be able to express this so we make it programmable. So what we say is we want a vector, in this case a column vector, of all the forces, and that will contain force 1 and force 2. We then want to say that is equal to some kind of a matrix multiplied by the displacements, which in this case is 1 and 0. Notice that the force vector is a 2 by 1 matrix, the displacement vector is a 2 by 1 column vector, and therefore the matrix must be 2 by 2. And you'll find I do this often through the course. It's a way of keeping track of what you're doing. Now notice here, which of those unknown elements can we fill? We can't really fill the second column because the second column would be multiplied by the 0. So that doesn't matter. And because it's 0 there, we can't fill this. What we can do is say, because that displacement is 1 there, we can fill these two columns. And when we look at what we must do there, to get force 1, we have to multiply what with 1? We have to multiply K. To get force 2, we have to multiply what with 1? We have to multiply minus K. So these two columns get filled with a K and a minus K. So the final step is to infer the element stiffness matrix. In other words, we look at what we've got here, and we can now, based on this alone, we can fill the first column of the stiffness matrix. In other words, the stiffness matrix K, the first column is K and minus K. Now we can continue to get the other column in the stiffness matrix. So we draw the spring again, but in this case, there is a displacement at node 2 and 0 displacement at node 1. So in other words, the displacement at node 2 must be in the positive direction, so it's stretching the spring, and you need a force at node 1 to oppose the force at node 2 so as to maintain equilibrium. As before, the force is simply K times the displacement of 1, so the magnitude is the same. But in this case, the positive K is at node 2, and the negative K is at node 1. So we can set up the second column of the stiffness matrix in this case. So the top one for node 1 being minus K in this case, and for node 2 being K. And when we build this into the stiffness matrix of the element, because we now have the second column, we get the complete stiffness matrix of that element. Note in particular that we have symmetry, right? The off-diagonal terms are all the same, and this is a characteristic of all stiffness matrices that you get from linear elastic elements, as you'll see through this entire course. Let's now consider a spring assembly. What we have here is 4 strings connected to 4 nodes. There's node 1. This is the entire block is node 1. In essence, the whole thing can only move in the x direction. So although it's a block, we regard that all as one node. There's node 2, node 3, and node 4. So notice that node 2 is fixed. It's a fixed boundary condition. Nothing can move there. Node 4 is a prescribed displacement. In other words, we are going to take that node and force it to be in contact with this surface over here. It's a prescribed displacement. This node has a prescribed force. There's a force F working on it. And this node number 3 appears to have neither a force nor displacement applied to it. But in that case, if there's no displacement, what we say is that it's a 0 force boundary condition. The next step is to generate the global stiffness matrix using the unit displacement method. So note, the boundary conditions can be ignored while generating the GSM. Okay, even though this has boundary conditions which are fixed and boundary conditions which are free, we're going to look at this entire assemblage as if it has no boundary conditions. We're just going to set up the stiffness matrix. In the next lecture, we'll consider how we actually apply boundary conditions. So don't worry about the boundary conditions now, just focus on the stiffness matrix itself. So how does one set up the stiffness matrix of an assembly using unit displacement method? Well, the first thing we look at is that we have 4 nodes, 1, 2, 3, and 4. Each have 1 degree of freedom, so we should have a 4x4 GSM. Now we must decide which one we're going to fix. We want to look at column 1, so we fix all of these nodes except for node 1, which has a unit displacement. So all of those are fixed, they stay where they are, but node 1 we're going to move by a unit displacement. So how do we do that? We can only do that if there are two forces being applied at node 1 because of those two springs. And the force we need to apply is K1 to move this spring and K2 to move this spring. So the force on node 1, in other words, the first number in our first column of our stiffness matrix must be K1 plus K2. The next thing we recognize is that both node 2 and node 3 have to provide resisting forces, otherwise these springs will not be in equilibrium. So we see that at node 2, we're resisting the force in spring 2. So in other words, that would be minus K2, while at node 3, we're resisting the force in element 1, so that has to be minus K1. Finally, we see that K4, spring 4, is not being stretched at all, so no resisting force is required at node 4, so the element or the number there is simply 0. Next, we can do exactly the same for node 2. We now want to look at column 2, so we fixed all the nodes except node 2. Now, even though node 2 is eventually going to be fixed, it's got a fixed boundary condition there, when generating the global stiffness matrix, we look at it as if it is free. So node 1, 3, and 4 will be fixed, while node 2 gets a unit displacement. For that to be possible, when node 2 moves, you have to stretch element 2 and compress spring 3. So that means that the force on node 2, in other words, the second block in the second column, must be K2 plus K3. To resist that force, to make sure that the elements 2 and 3 remain in equilibrium, there must be negative forces at node 1 and node 3. So node 1 gets a minus K2, and node 3 gets a minus K3. And again, there is no force on node 4, so that final bit is 0. Following the same procedure, we now look at column 3 of the stiffness matrix, which relates to node 3. So, as before, in this case, node 1, 2, and 4 are fixed. Node 3 gets a boundary condition or a displacement of 1. And in this case, there's 3 forces acting in on it. To cause that displacement, you have to stretch spring 1, stretch spring 3, compress spring 4. So you'll have 1 plus K3 plus K4 at the third point of the third column. There must be resisting forces at all the other nodes to prevent the movement. So at 1, it'll be K minus K1, at 2 minus K3, and at 4, in case it's not 0 in this case, it must be minus K4. So we have all of those other elements filled. Finally, we consider column 4. We ignore 1, 2, and 3 as not moving. Node 4 gets a unit displacement. To create that displacement, you need to stretch element 4, so that simply gets a K4 in the last block of the fourth column. Only node 3 has to provide a resisting force, so only node 3 gets a minus K4, while neither of these spring elements are being stretched, so both node 1 and node 2 need to offer no force whatsoever. And in this way, we've now assembled or calculated, extracted the entire stiffness matrix for this spring assembly. Notice that the global stiffness matrix, all its off-diagonal entries are symmetrical. And as mentioned before, this is characteristic of all stiffness matrices that are produced via linear elastic finite element analysis. Furthermore, notice that the diagonals are all positive and non-zero. If you see a negative or a 0 entry on the diagonal, something has gone wrong. Next, we're going to consider an alternative approach to generating the global stiffness matrix using element stiffness matrix assembly. Now, the reason we have to do that is because it's difficult to get a computer to implement the unit displacement method. Furthermore, the unit displacement method doesn't work for all elements, so we need an alternative approach. So instead of considering the entire assembly or mesh at one time, we're going to consider each individual element and see whether we can build it in or assemble it into the global stiffness matrix. So let's start with element 1. The stiffness matrix for element 1, if we were only considering element 1 by itself, would be this: minus K, minus K1, minus K1, K1. Now those entries into that stiffness matrix are associated with certain nodes, namely nodes 1 and 3. So we can expand the size of this matrix to the size of the global stiffness matrix as follows. So there we've taken it from a 2x2 to a 4x4, and we keep track of which nodes are they associated with and put these entries into their appropriate places. We don't know what the rest is, so let's just fill them with zeros. Notice that when the matrix is the size associated with the element itself, or the degrees of freedom of the element, we use the small k, and when we expand that to the degrees of freedom of the entire mesh, we'll use a large K. We can now do exactly the same thing for element 2. There's element 2, it's connected to nodes 1 and 2, so when we expand that, we get a matrix that looks like that, and all the rest are 0. We can do exactly the same thing for element 3 and element 4. Element 3 is associated with nodes 2 and 3, so it'll be this middle block over here. Element 4 is associated with nodes 3 and 4, so it'll be this last bottom right block over there. And in that way, we've now expanded all the element stiffness matrices to the size of the global stiffness matrix, and we've simply added zeros where a particular element has no effect. And we can now add them all together. In other words, the global stiffness matrix K can be written as the sum of all the individual element stiffness matrices expressed in the same size as the global stiffness matrix. Notice that we can't do this with the small k matrices. We can't simply add those together because they're referring to different degrees of freedom. But once we've expanded it to the size of the global stiffness matrix, all those degrees of freedom correspond, and we can add them together. So there we have the first element, second element, third and fourth element. And you simply add those together, and what you get is the global stiffness matrix. And notice that this is exactly the same form as we achieved with the unit displacement method. We only achieved it by adding the elements together. We literally expand each element stiffness matrix to the size of the global stiffness matrix and stack them on top of one another, and you get the global stiffness matrix. When we finally get to programming our finite element code, we're of course not going to expand each individual element stiffness matrix. That simply takes too much time. Rather, we're going to recognize that, for instance, element 1 has those elements, and we're simply going to take each individual entry and put them in the right places in the global stiffness matrix. Similarly, element 2 has those entries, and we're going to take those individually and add them where they need to go. Similarly, node 3, the yellow one, those are its entries. It'll go in those places in the middle, simply add them in. And similarly, node 4 in blue, those are its entries, and they will go in the last place over there. And we'll do it entry by entry when you practically come down to implementing this. So let's summarize what we've covered in this lecture. First of all, we've seen that a 1D spring element can be described by a 2x2 matrix. We generate that element stiffness matrix using the unit displacement method. In other words, we set all degrees of freedom to 0 except one, which we set to unity. Then, calculating reaction forces, those all provide a column of the element stiffness matrix for that given degree of freedom that we have set to unity. However, to use this approach, each element must be based on an analytical solution. We know what the solution is for a spring. Now, most of the elements we're going to deal with in this course, there is no analytical solution. And so we have to use some approximate method, and that's what most of this course will be based on, namely the approximate methods by which you can build element stiffness matrices. Nevertheless, having generated those element stiffness matrix, we can generate the global stiffness matrix by element stiffness matrix assembly. In other words, we add the element stiffness matrix row and column to the global stiffness matrix according to the global degree of freedom. We can envision that, we can imagine that by taking the element stiffness matrix, expanding it to the size of the global stiffness matrix, and then plugging it in. But in practice, what we're going to do is going to go through each element or each entry of the global stiffness matrix, take it out and put it in the global stiffness matrix at the appropriate place that corresponds to the right row and column, which is associated with those degrees of freedom. And how we do that and how we then solve it will be the topic for the next lecture.